right? Because purple is dominant, okay? So, and then that's going to dominate, and that's going to be the color of that flower, all right? And so then what's going to happen if we then take these and cross them to each other, okay? So now it gets a little more complicated because what it means is that half the gametes will have big P and half the gametes will have little p, all right? Because gametes will randomly get one or the other allele. And so if we then do that, then we draw this little Punnett square, right? And we say, okay, so the sperm from one plant are big P, little p, okay? And the sperm from the other, from the eggs that are made are also big P, little p. And then they combine, and they can combine in 4 combinations that are shown here, okay? And we can get big P, big P. These 2 combinations give us little p, or sorry, big P, little p. And this one here gives us little p, okay? Does everyone, that's all straightforward? And so then we can ask, well, what the color of these plants, of these flowers is going to be. So obviously these are going to be purple. They're going to be like this grandparent all the way up here, right? And then these 2 are also going to be purple, okay? They're going to look just like this, though actually in terms of the alleles they have, they're like this parent here. And then there's going to be 1/4 of them that are little p, and they're going to be white. So they're going to be white even though none of their parents were white, okay? But in fact, a grandparent was white. And the reason it's white is because it's ended up with 2 copies of the recessive allele, little p, okay? And that's the gist of the way that this works. And from that little bit of knowledge of how to do this, you can actually predict really, really complicated crosses as well, even though the real world gets pretty messy. So we'll go through more examples on how this would work, all right? So, and then other vocabulary that we use is that we say that an organism is homozygous for some trait if the 2 alleles are the same. So if the both little p, we would say that it's homozygous for little p, okay? Likewise, it's heterozygous if it actually has the 2 different alleles. So if it's big P, little p, we say that animal is a heterozygous animal, okay? And so homozygous would be true breeding for that trait. So if we had an animal as little p, and we just fertilized it to itself, then of course it would just be true breeding white flowers. But that's not going to be true for heterozygous because then in the next generation, you're going to get a combination of the 2 alleles. Both 2 copies of the dominant or 2 copies of the recessive will sometimes occur. So you'll get different traits showing up, okay? And then because of this dominant-recessive relationship, then it means that you can't always tell the genetic composition of an organism from the traits that it has. Or another way of saying this is that its genotype, its genetic makeup, you can't always know that just from its phenotype, okay? From, for example, the flower color. So if I showed you a purple flower, okay, how would you know whether it was big P, or big P, little p? Okay? So you couldn't know just by looking at it, but you could know if you mated it to another flower, okay? So if you mated it to itself, since you can self-fertilize it, if it was big P, then all the progeny would be purple. But if it had been big P, little p, it would have looked just like the other one that you had. But now when you made it to itself, right, you would get a ratio of 3 to 1 of purple to white flowers, all right? So then you would know that its genotype had been as a heterozygous, right? But you wouldn't have known it from its phenotype, okay? So you can get different ratios if we consider phenotype versus genotype, okay? And that's shown here. So if we have these flowers, and this would be the F2 generation, we would say that the ratio of phenotypes was 3 to 1, because there's 3 purple flowers for every 1 white flower, okay? But if we could look at the genotype, so if we could look and actually assay what alleles it had some other way, we would see that, in fact, it's 1 to 2 to 1. So it has a ratio of 1 big P, and then 2 big P, little p, and then again 1 little p, okay? But the reason the phenotype and the genotype ratios are different is because all of these are purple, okay? So we're not able to see that there's different genotypes in the phenotype. Right. Does that all follow? All right. Okay. So, all right, how well can we tell the genotype of an individual with the dominant phenotype, okay? Or how can we tell the genotype of an individual with a dominant phenotype? And again, the idea is to do a test, what we call a test cross. So there are a couple ways to do it. I talked about if you bred it to itself is one way, but the standard test cross is to breed the mystery individual with a homozygous recessive individual, okay? So that means if I had a purple flower, what I would do is I would mate it to a white flower, okay? So, and then think for a minute about what the outcome would be, okay? So take a second to write out that cross for yourself. So again, you're taking a purple flower, mating it to a white flower, but you don't know if the purple flower is big P, or if it's a big P, little p purple flower. And you're going to mate it to a true breeding white flower, okay? And now you're going to look at the offspring, and you should be able to tell me then what the difference would be in the progeny given the starting genotype of the purple flower. Okay, don't wait a second. Let everybody get a chance to think about it. Okay, so you should see that you're going to get 2 different outcomes, all right, and that's shown here. So if I do this, right, and I breed this purple flower to this white one, if this purple flower was big P, then all of the offspring are going to be big P, little p. They're all going to be heterozygous, okay, and they're all going to be purple because they have at least 1 copy of big P. Okay, so then I'm going to get all purple offspring. But if this purple flower were big P, little p, and I mated it to this white flower, then I'm going to get this ratio in the next generation. So now what's going to happen is that this parent, let's say this was the female, the eggs will be big P, little p. Okay, so half the gametes will have big P, half the gametes will have little p. But the purple flower, all the gametes will be little p, little p. Okay, or sorry, they'll all be little p. Okay, and so then when you look at the Punnett square and you see what combinations you see that you can get big P, little p, okay, from those combinations, and you get little p from those combinations. So now you get a different ratio. You get a 1-to-1 ratio of purple to white. All right, and so that tells you then if you get this, that this flower was big P, little p, was a heterozygous instead of a homozygous. All right. Okay. And it seems like, it often seems very boring to show it with a P example, right? But this basically holds for all sorts of what we call Mendelian traits, and most traits, or many traits, and we'll go through examples, are inherited this way, all right? Okay, so then the other thing that Mendel noticed or observed, and then came up with a sort of a rule about, was the law of independent assortment, okay? So he said, well, what if we're looking at more than one character at a time, okay? So we've just given you examples of flowers, right? And shown you what happens if a purple flower and a white flower. But what if we have, if we now start looking when there's 2 different characters that we're following, okay? And so these were called dihybrid crosses. So the plants, let's say, we'll give an example in a second, so they could vary in 2 different traits, okay? And be true breeding, but now he was going to make a cross between those. Right? And so this is the example that we'll start with. And so now we're looking at the P's instead, right? But there's 2 traits here. One is the color of the P, yellow versus green, okay? And the other is the shape of the P, smooth versus rough, okay? And so you can have a true breeding yellow smooth P, and we call that big Y, big Y, big R, big R, okay? So those are, you have a P like that. And then you can have a P that's a true breeding, and it's a recessive trait, so it's little y, little R, little R. And that's a green P that's rough, okay? And so again, if you just mated these to each other, these would all continue with this trait, these would all continue with that trait. But if you make the cross, okay, what you're doing now, and the best way I think to learn this is just to write these out for yourself. I mean, I can go through these and show them to you, but until you sort of force yourself to do them on your own and just write it out, it's hard to really learn them. So what's going to happen is that you can look, and what you get is independent assortment of these traits. So you could imagine that what would happen was that you didn't inherit these traits independently. So a sperm, for example, would be big Y, big R, or little y, little r. All right? But that's not the case. What can happen is that the traits segregate independently of one another. So now when we think about it, the sperm, there's 4 different types of sperm that you could form. You could form, and we'll talk about, sorry, from the F1 generation to the F2. So now we're looking at this P, which is yellow and smooth, and it's big Y, big R, little r. Okay? And so now what you see is that you can have sperm that are going to be big Y, big R, little y, big R, little y, little r. Okay? So you can get all the combinations that are possible. All right? So you can write out your Punnett square of those different sperm, those different eggs from this F1. All right? And you'll see that you can then get these 16 different genotypes that you can write out here in terms of this Punnett square. And then you can look at this, and you'll see that the phenotypic ratio is 9 to 3 to 3 to 1. Okay? So 9 of these outcomes will be like the F1. They'll be yellow and smooth. Okay? And then you'll get 3 and 3 equal numbers of green and smooth and yellow and wrinkled. Okay? And then the rarest one will be this one here, which is the homozygous for the 2 recessive traits. Okay? Little y and little r. So this one will be green and wrinkled. All right? So you should work through this yourself and make sure you can see that. All right? And from this, right, Mendel deduced, because he got this outcome and not this outcome, all right, he deduced that this law of independent assortment, okay, so that the pairs of alleles segregate independently of each other during the formation of the gametes, during sperm and egg formation. Okay? And this is where Mendel got a little bit lucky, because it turns out this is not totally true. We'll explain why it's not totally true. But there's various debates as to how he got lucky with this, whether he cheated and eliminated some data that didn't quite follow the ratios that he was predicting, or whether it was really just luck that he got 7 traits that were far enough apart from one another that they segregated independently. And we'll talk about why when they're close together on a chromosome it makes a difference. Okay? But for right now, you can just always think of these as independently segregated, and we'll get to the exceptions later. Okay? So in a sense, strictly speaking, this law only applies to genes that are on different chromosomes, okay, or when genes are far apart on the same chromosome. But for today and the problems we're going to work out, you can assume that they're segregated independently. Okay. So and then what Mendel realized then, and this was probably the big conceptual breakthrough, is that you could actually make a mathematical prediction of what the outcome would be. Okay, and he realized that it was just there were just rules of probability. That you had this unbiased partition into gametes, and then you had independent assortment, and so you could use the rules of probability to determine the outcome. Okay, the probability of an outcome. So if you're asking, you have one single progeny, right, in a dihybrid cross, right, from an F1 to an F2. I can't tell you exactly what the phenotype of that is going to be, but I can tell you what the probability of it is going to be. Right. So if I go back to this, and I just had one progeny from this cross, okay, in the F2. So if I just had big Y, big R, little r, across of those, and I only had one P to look at. Okay, I couldn't tell you for sure what that was going to be, but I could tell you what the probability was of any given phenotype. Okay, does that make sense? Okay, if I have enough of them, I can be fairly accurate in determining the ratio. Okay, and that was also part of Mendel's one of his strengths was that he did enough crosses. I think the estimate was, if you read his paper, he bred something like 29,000 pee plants, okay, in order to collect all the data that he had. Because you can imagine that if you'd only gotten like 4 Ps out of this cross, you'd have a hard time realizing what the ratios are. Okay, because then you have a problem. It'd be like tossing a coin. I mean, a couple times, you wouldn't necessarily end up 50-50, but if you toss the coin 1,000,000 times, you'd probably be pretty close to 50-50. All right. Okay, so all right. And so it turns out that if you start doing more and more complicated crosses, you don't need to keep drawing more and more complicated Punnett squares. That in fact, you can use some simple rules to answer the questions and to come up with the probabilities. Okay? And it's by knowing the probabilities for any one allele and then adding them up or multiplying them as appropriate for the other alleles, for each allele independently, you can come up with a probability. I'll give you an example here in a minute. Okay? So, so imagine then again that you have a situation here where you have the heterozygotes and you're mating them, right? So we know that you'll have a quarter that are homozygous for the dominant allele. We'll have half that are heterozygotes, and we'll have quarter that are homozygous. So then this is like flipping coins. If you had only one offspring, we could say what the probability of that was. So if we only had one flower, let's say one progeny that formed from this, and we asked what the phenotype would be. Okay, let's just for now let's go back to this being big P and little p, so purple flower. And so we have a heterozygous purple flower, and we do this cross, and I just get one plant out. Okay, what's the probability that that plant is going to be purple? Right. Okay, 75%. Does that make sense? So I can't know for sure what it's going to be, and there's a 1/4 probability that it's going to be white. All right. If I had like 10,000 progeny, I'd probably be pretty close to that ratio. If I just had 2, right, I could end up with 2 white plants. Right? And you can calculate the probability of that. It's not unreasonable for that to happen. All right. And that's again why you need the numbers to make the prediction. Okay. But we can also then add up probabilities, and we can figure out what the probability of more complicated outcomes is going to be when we have multiple alleles that are segregated. Okay. And so we can take F2s that are not just monohybrids and that have multiple alleles, but we can treat them as the outcome of all the different monohybrids and then come out with a probability. And it'll be easier if I show you examples in just a second. Okay. So the idea is that we can just apply fairly simple math, and we can come out with probabilities of much more complicated processes by doing relatively straightforward multiplication and addition. And that's what Mendel realized, is that in fact he didn't have to then draw like a giant Punnett square to figure out if he had all 6 different alleles that were segregating, and he knew whether the parents were heterozygous or homozygous. He could predict the probability of any outcome. Okay. And so this is an example. Okay. So let's say I have this cross right here. Okay. And I just ask you what the probability of getting big Y, big R, big R is. Okay. So that would be that would be the genotype I'm looking for. And so I don't have to draw out a big Punnett square. I can say, okay, for Y, okay, the probability of being big Y is 1/4. Okay, does that make sense? All right. Likewise, the probability of being big R is also 1/4. Okay. And that should be pretty straightforward. And that means that the probability of being big Y, big Y, big R, big R is 1/16. Okay, so it's the product of those two probabilities. Okay, so something that's 25% probability and a 25% probability, then in the end that's a 1 in 16 chance of getting that in the progeny. Okay, so likewise I could say, well, what's the probability of getting big Y, little y, big R, big R? Okay, so big R is still the same here. There's a 1/4 chance of getting that. Okay, but then the probability of getting big Y, little y is 1/2. Okay, so then this probability is 1/8. Okay, so we'll pick up from there